Okay, let's see the problem for today. It's still about tree max path. So given a valid tree T in array representation like this, it's an array and then start with the parent node and then the left child and then the right child and then left child of this left child and then right child of the left child and then left child of the right child and right child of the right child and so on. So for you who don't know yet, this is one of the data structure representation of tree that is quite efficient, right? And um, easy to process, easy to represent. But you need to always remember that, as my previous video before, regarding the map indices to parent tree, it needs to follow the pattern of 2 times parent index plus 1 for the right child, for the left child, and plus 2 for the right child. Like this one, right? It starts with index 0, it's the parent. So the left child index for it must be 2 times 0 plus 1, right? Which is 1. And the right child, 2 times 0 plus 2, which is 2, right? And if we want to get the oops, the left child of this, the left child of the left child, right? 2 times 1 plus 1, which is 3, right? 0, 1, 2, 3. You get the left child of the left child. Same thing for the right child. Plus 2 becomes 4, right? 0, 1, 2, 3, 4, and so on. So this kind of pattern represents the binary tree, especially in this kind of data structure. Okay, now what task do we need to do here? Find the maximum path from leaf of highest price. So now the tree has a price, right? Each node has a price that that it carries with it to another leaf. So from one leaf to the other leaf. The program should return the path sequence and the total maximum price for the path. Okay, let's look at the example. We have this kind of tree. If it's these are the prices, right, inside the node. These are the indices: 0, 1, 2, 3, 4, 5, 6, and so on. Okay, so if the input is representing the tree, which is start with 2, 2, right? 2, 2, 2, 2, 4, 3, 4, 3, then 1, 2, 1, 2, okay? And the output should be the path sequence with the total maximum price from leaf to leaf, okay? So it should be 3, starting with this 3, right? 3, and then 1, and then 0, and then 2, and then 6. And also it should print out the total price for that path, which is 12, right? 4 plus 2, 6 plus 2, 8 plus 2, 10 plus 2, 12. Okay? So that's the desired output that we want to have in the program. Alright, and the path sequence should start with the highest price. That's why it should be 3, 1, 2, 3, 1, 0 to 6, and not starting from 6, 2, because 4 is greater than 2. So it should always start with the highest price, leaf of the highest price to another leaf, right? Okay. Example 2 is quite a simple tree. It's just 3 nodes, 2, 1, 3. So the output should be 2, 0, 1, right? Again, because the index 2 has the higher price compared to index 1, which is 3, and the total of it is 6. 3 plus 2, 5 plus 1, 6. Okay, there are some constraints. So the tree length between 1 until 100,000. The Ti is the price of a node. Ti can be 0 and null. 0 and null. This I think an important constraint as well to consider. And the array given from the test data or for the input are always a valid tree. Okay, so let's pause a second. I think the problem is quite clear now. Try to squeeze some brain and try to solve the problem by yourself before continuing the video. All right, so I will proceed with the solution. So how to find the maximum path, right? For this, I don't think there is another way to solve it but using the depth first search, because we want to get to the leaf as soon as possible, right? Compare it to that leaf's parent node, which one is bigger, and then we record that node to be included into the path that we are going to print out in the program, and also accumulate the price of the node for the program to return, right? All right, so let's see the program. Okay, we have the main program called findMaxPath, and we have the DFS inside, right? We have as well the generate child tree to generate a child tree from the parent tree. Okay, and then we also have map index to parent tree. So this is the function that is similar to the previous video that I talked about. So make sure you check that in order to follow, because I am not going to explain it here again. Okay, these are some test data that we are going to look at later. So find the max path. First, if the tree length is 1, and that is the minimum length of the constraint that we have here, so we just need to return that node, right? And the price of the node, which is by accessing the array value of that node, of that index, right? So we return the path, which is the node itself, and then the price. Okay, and then we are going to store the child maximum index, because we are going to compare between the left child and the right child, or the far distance child. Like for example, yeah, here if the prices are different, it could be the you have the maximum path looking from the parent node, right, this way, right, this side, but you have the second path from this side, right? So then you need to first store. You cannot go traverse like to both sides together. You need to traverse on one side, right, to know which path is longest for this child, right? Either this or that. And if the tree is big enough, then you will have a kind of hard to know which path exactly that it gets from the root node to the leaf maximum price node, right? It could be from here, and then the second longest is this one, right? So you need to store the information of the child maximum index, so then you can later on go to the second maximum. Okay, and then here we run the depth first search for the tree, and the parameters for it is first is parent index, and then the tree, right? We pass the tree, then we get in return the maximum sum, which is the total price for it, and the maximum paths, right? Okay, so let's stop for the main program in the line 11. Let's go to the depth first search function inside it. So parent index and tree, because this function is positioned inside the find max function, so I want to distinguish between this tree and this tree inside, so that it basically, if in JavaScript it has this closure mechanism where if we declare the same variables, it still take the closest declared variable for the function. But just to make sure that these are the different variable, right? So I make different naming for it. Even if you put this like this, it will also still work. Okay, let's see parent index and then tree. So we are going to have a variable to store the paths, right? And then the left index, as I explained before, it will always be 2 times the parent index plus 1. Right index is plus 2. Okay, and then if we need to somehow terminate, because this is the depth first search and you are going to go through a recursive calls, we need to find a way how to terminate this recursive calls, right? And we go by this one. If the left index has exceeded the tree length, because the tree length, this multiplication, right, will always dependent on the tree length. So by some sort, you will stop the left index before the tree length. Like for example, if you have the 3 nodes tree like this, right, the left index stop at 1, right? 2 times 0 plus 1 is 1, and that is 2 numbers before the tree length, which is 3, right? And the right child of it is 1 number before the tree length. So because the calculation that we have is 2 times parent index plus 1, we could identify if whether the program has run out of the bound with this simple check. Because if the left index has exceeded the tree length, of course the right index also exceeded the tree length. So we check by that first. Or if parent index is less than 0, if parent index less than 0, right, it means it does not qualify a valid tree. We just return this. First thing is 0, and then parent index less than tree length. We check whether the parent index less than tree length. If yes, we are going to pass the parent index, right? If not, it's just an empty array. Okay, let's go on. So what is the left child of it? Left child is the 3 and then access the left index, right? Left child means the price of the left child here, or 0, and the right child also we access like this, and then we are going to compare, right, between the left sum and the right sum. So imagine like we have 3 nodes only, and this kind of sub problems will be valid also for the bigger problems, the whole tree. So we will have the left sum and the right sum, right? And we are going to compare them. So we will call again the DFS for the left child with now the parent index become left index, right? And we are going this, to pass the same tree, and the right sum also the right index, right? And we get in return the sum and also the path. Okay. And it will stop, basically the sum here is for anything below current node, right? Which is the children that it has that generates the max path or max price, right? So if you want to calculate with current node, we need to add by its price or its value itself. So we have left child plus left sum here, and the right child, the value of the right child plus the right sum. And to find the maximum sum between the left and the right, we just simply compare it with the maximum method of the math library between the left and the right, right? If max sum is equals to the sum left, so meaning we know that it comes from the left child, right? We update the child max index to be the left index, okay? And then the paths will be will be all the leaves nodes. That's why we spread out the children first before the parent, because we are going, if as you see again, we should print out from the highest price of the leaf, right? So leaf, the leaf first, and then at the middle it would be a parent node, and then to the other second maximum path from the parent to the leaf. So that's why we construct the array like this. So we are going to take the leaves first, and then append the parent node. So it will always going up, right? For the left child, if the maximum sum comes from the left, and the right, if it comes from the right child, we update with the right index, and then also right child paths, right? That comes from the right index DFS. Okay, and then at the last of the DFS or depth first search function, we are going to return the maximum sum and also the paths. Okay, so we stop at line 11 before here. So we got the maximum sum and so max paths, right? And then now we are going to compute basically the other path that generates the second max, right? But before we store the result first, again the max sum here, remember from the DFS is all the max price and max path or max sum and the max path generated for its children, right? It does not include the node or the parent node in this case, right? That's why on the result we need to add the parent price here. Okay, after getting that, basically we need to add again later with the second max path price, right, or sum. Then here we are going to compute the second max path from the other child. All right, then what is the second index? Basically it's about the same, right? If the child max index coming from the left child, right, the second max, that it will generate the max path, right, must come from the other side of the child. So it is what implied here. So if it comes from the right, when we mod by 2, then the remainder is 0. So the child max index would be the left one, and the difference between right and left would be by one number. So if it's right, we minus 1, that means it's the left child of it. And if it's not the right child, then it must be left. Then the second path must be the right child. Then we plus 1. Okay, so that's how we get the other index to traverse to get to the other leaves, right? And then the child tree. Why we need the child tree here? Because we want to traverse all the way to the new second path, right? Then the simplest way to do it is to call the same DFS, but with this child tree that we are going to generate, right? And then so we make the child tree, getting the first is the parent index of it, right? And then generate the child tree for that tree, starting with this second path. And let's go to the function generate child tree. Okay, so we learn many things in this problem. So to generate a child tree, basically we will evaluate whether the tree keys includes the new parent node or not. If it's not, then just return empty array, right? Basically, because we cannot generate the child tree for this kind of input. We are going to be able to generate a child tree if the new parent node indeed exists in the tree, right? And then left index, would be the same. New parent node times 2 plus 1, right index plus 2. If the tree left index is undefined, right? And then we check again. If the tree right index undefined, return empty array. Why? Because we need to cater for the null case here, or undefined case of the child, right? As the constraint stated. And else, if the left child is null, but there is a right child, right? We are going to return those. So this kind of thing. So the left index will be null or undefined, but we have the value for the right child, right? If both null, then you do not need to do anything. That's why it's returning this empty array. Nothing that you need to concatenate to the rest of the tree or child tree generation. You will just need to return in case that the left child is null or undefined, but you still have the value for the right child. Okay, and then if the left index exceeded the tree length, again we are going to stop the recursive calls, right? We are going to return empty array as well here, and the final return is the whole thing, which is take the left index, right, and then take the right index, and then the child tree from the left index, which is this one, and then the child tree from the right index, right? This one. And again, remember that this does not include the current node or the root node that we are passing here. That's why, if you still remember, on generating the child tree, we need to pass the parent node here and then getting the other nodes. Right. Okay. So now we already generated the child tree for the second path, and we are going to do the DFS, the same exact function, but now with a different tree, with a child tree, and we are going to pass the parent node as 0, right? Because the parent node will always be 0, and then we need to translate this to the indices of the original parent tree, right? And from this DFS, we are going to get the other maxsum, which is the second maxsum that the path will have, and the second path, right? And somehow this second path will be generated from leaf to the parent node that we are passing, right? While on the last or the final return, we are going to have something in reverse, right? Like his from 0 to 6, right? And that second path traversal basically will generate the 6-2, right? 6-2. So we need to to reverse that and then append it to the first maximum path. So that's why we have the reverse here. And then second path, we need to map the index to the parent tree, because again, remember that we are remapping the indices here to the child tree index. We need to map the index that we get here on the second path to the parent tree, right? And then this will be we are going to pass the reversed indices, and then by getting the by passing also the index second path, we are going to get the second path in the original parent tree. So if you want to dig more on this function, please check my previous video on map indices show parent tree for explanation in detail, right? And the result, right, the previous result that we have for the price is until the parent node, and then we need to get the other path, which also need to add the parent node for that child tree, which is the index for the second path, price, and then the other maxsum that we got from the DFS here. Okay, and last thing is returning the whole thing, right? Which is the path first. We are going to destructure the max path and then the second path. The max path include the parent node. The second path does not include, because we are taking the parent node for the DFS for the starting with the second second child, right? Second child, and then giving it the result in return. Okay, let's try out. All right, we pass 10 over 10. Let's see the duration 5.2 millisecond for case 11. I think because the number is quite big. This is 5.2 millisecond 0. Okay, let's see. 1.3 165, which is this one, I think. Solved in 1.3 millisecond. And on linear prediction, 1000 nodes that the constraint has should be solved in around 814 milliseconds, still less than 1 second. which is good enough, right? So let's test again. See, like this kind of having a null value, it's still returning the correct path. All right, I think that's all for this problem. If you find another way how to approach it, please let me know in the comment so that the audience and the viewers can also learn from the other solution on how to solve this problem. Thank you. See you on the next problem.